All right, so I'm back. What's the date today? So today is 1st of June, and I'm actually back after a long time. I was I was not on the track since these maybe these 10 days, 10 11 days because I was pretty much distracted. But guess what? Guess what? This book saved me and I'm back on the track. I have reread this book one more time and yeah, I'm getting pretty much back on the track, just trying to make sure that I'm consistent with this video lectures and the problem solving that they're providing on their platform on the MIT Open Courseware. So let's just get started. And well, today we're gonna you must have uh, saw the title of the video that today we are going to study probability. I did recorded the other lectures. Well, wait. Let me just get back. Um, wait. Let me just see my channel, viewer channel. So I did lecture 3. I did recorded lecture 5 of the Python, and I also recorded the reading material for the probability. I think it was 2 weeks ago. No, not 2 weeks exactly. I guess it was on last Monday, as far as I remember. Oh, it was on 25th, and I was not. But as I just said, that I was not very much consistent last week. But anyways, I have to do some editing in those videos, and then I'm gonna post those videos. So let's just get back
The
to
following content
let let me just open my Epic Sound. So
is provided under a Creative Commons license.
yeah,
Your
that's better. And let me hide this up so I don't accidentally stop my recording. Okay.
support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Okay, so today's lecture will be on the subject of counting. So counting, I guess, is a pretty simple affair conceptually, but
Let me just open my laptop. I just have to make sure that I'm not giving any time over 2 hours. I guess, yeah. So we'll be getting up at 5:30, exact 5:29. Yep. Okay.
it's a topic that can also get to be pretty tricky. The reason we're going to talk about counting is that there's a lot of probability problems whose solution actually reduces to successfully counting the cardinalities of various sets. So we're going to see the basic, simplest methods that one can use to count systematically in various situations. So in contrast to previous lectures, we're not going to introduce any significant new concepts of.
So this is what we are going to study. It's a principle of counting, permutation and combination. I guess that's what they're talking about, which we eventually study in our high school. And examples of permutation, K permutations, combinations, and partitions, and binomial probabilities. Okay.
The probabilistic nature. We're just going to use the probability tools that we already know, and we're going to apply them in situations where there's also some counting involved. Now, today we're going to just touch the surface of this subject. There's a whole field of mathematics called combinatorics, where people actually spend their whole lives counting more and more complicated sets. We were not going to get anywhere close to the full complexity of the field, but we'll get just enough tools that allow us to address problems of the type that one encounters in most common situations. So the basic idea, the basic principle is something that we've already discussed. So counting methods apply in situations where we have probabilistic experiments with a finite number of outcomes, and where every possible outcome has the same probability of occurring. So we have our sample space omega, and it's got a bunch of discrete points in there. and the cardinality of the set omega is some capital N. So in particular, every point we assume that the sample points are equally likely, which means that every element of the sample space has the same probability equal to 1 over n. And then we're interested in a subset of the sample space, call it A, and that subset consists of a number of elements. Let the cardinality of that subset be equal to little n. And then to find the probability of that set, all we need to do is to add the probabilities of the individual elements. There's little.
So there are actually four, so it should be 4 over n. No, 4 over n, 4 over capital N, because the probability of each discrete points is 1 over capital N.
Little n elements, and each one has probability 1 over capital N. And
Okay. Okay, all
that's
right.
the answer. So this means that to solve problems in this context, all that we need to be able to do is to figure out the number capital N and figure out the number little n. Now, if somebody gives you a set by just giving you a list and gives you another set, again giving you a list, it's easy to count their elements. You just count how much there is on the list. But sometimes the sets are described in some more implicit way, and we may have to do a little bit more work. There's various tricks that are involved in counting properly, and the most common one is to, when you consider a set of possible outcomes, to describe the construction of those possible outcomes through a sequential process. So think of a probabilistic experiment that involves a number of stages, and in each one of the stages, there's a number of possible choices that there may be. The overall experiment consists of carrying out all the stages to the end, and the number of outcomes is the number of points in the sample space is how many final outcomes there can be in this multi-stage experiment. So in this picture, we have an experiment in which at the first stage, we have 4 choices. In the second stage, no matter what happened in the first stage, the way this is drawn, we have 3 choices. No matter whether we ended up here, there, or there, we have 3 choices in the second stage. And then there's a third stage, and at least in this picture, no matter what happened in the first 2 stages, in the third stage, we're going to have 2 possible choices. So how many leaves are there at the end?
So, if I count this particular node, this particular one node has 1, 2, 3, 4, 5, 6, and there are 4, so 6 times 4, 12, 24. There must be 24 endpoints
of these 3. That's simple. It's just the product of these 3 numbers. The number of possible leaves that we have out there is 4 times.
Okay. 12 times 2, 24. Okay. Okay.
Times 3 times 2. Okay. Number of choices at each stage gets multiplied, and that gives us the number of overall choices.
So that's a really good thing to notice if we are encountering a symmetric, so if we just look at this particular probabilistic model, we see that it's symmetric no matter what, as he mentions that there are 3 nodes. Sorry. So there are 2 nodes over this node. No matter what was the previous outcome, if we would be here, then it would still be 2 outcomes. So I'm just going to write that down. Symmetry is probably one of the best things that you can use in mathematics. Okay.
choices. So this is the general rule, the general trick that we're going to use over and over. So let's apply it to some very simple problems as a warm-up. How many license plates can you make if you're allowed to use 3 letters and then followed by 4 digits?
The number of license plates with the 3 letters and 4 digits. Okay.
You have, at least if you're dealing with the English alphabet, you have 26 choices for the first letter.
Okay. Let me just get that on my OneNote. So they're saying that, you know, the total number of license with the 3 letters. So for alphabet, we are using only 3 letters. For number, we are using 4 digits. What is the length of a license plate? I don't know. What is ELEG? Length of a license plate. Okay. So a license plate is okay. So I wasn't according to this particular image, a license plate is actually made up of three alphabets and 4 numerical digits. Okay. So we have 0, 1, 2 till 9. So that's 10, but we have to choose only how much? So 4. So that should be 10c4 times how many alphabets do we have? We have 24. C, how many we're supposed to choose? 3. So I think that should be the final answer. 10c4, that's 10 times 9 times 8 times 7 by 4 into 3 into 2 into 1 times 24. So 24 times 23 times 22 by 3 times 2. Okay, so 3, 9, 3. This gets cancelled out. 4, 2, 8. So the final answer should be 24 times 23 times 22. 22. Let's not write that. 22. Let me just cancel that. That should be 11 times 11. So these are done. Times 7 times 10. So that should be total number of possible outcomes that we could get. I think so. I'm not pretty sure about this. That's a guess.
Then you have 26 choices for the second letter.
Wait.
And
26. Oh, my bad. I think I did a mistake. Not 24. Should be 26. Okay, so this whole calculation is crap. This whole calculation is wrong. Okay,
and then
anyways.
26 choices for the third letter. And then we start the digits. We have 10 choices for the first digit, 10 choices for the second digit, 10 choices for the third, 10 choices for the last one.
Oh, okay. So, no, wait. Okay, I did some mistake. I probably did some mistake over here. I think my principles of counting is not clear. Okay, we are anyways watching that video over here.
Okay, let's make it a little more complicated. Suppose that we're interested in license plates where no letter can be repeated.
Repeated. So in that case, the answer would be this.
And no digit can be repeated. So you have to use different letters, different digits. How many license plates can you make? Okay, let's choose the first letter, and we have 26 choices. Now, I'm ready to choose my second letter. How many choices do I have?
25.
I have 25 because I already used one letter. I have the 25 remaining letters to choose from. For the next letter, how many choices?
24.
Well, I used up 2 of my letters, so I only have 24 available. And then we start with the digits. 10 choices for the first digit, 9 choices for the second, 8 for the third, 7 for the last one. All right. So now let's bring some symbols in, a related problem. You are given a set that consists of n elements, and you're supposed to take those n elements and put them in a sequence. That is, to order them. Any possible ordering of those elements is called a permutation. So, for example, if we have the set 1, 2, 3, 4, a possible permutation is the list 2, 1, the 3, 4, 1. That's one possible permutation. And there's lots of possible permutations. Of course, the question is how many are there? Okay.
So how many are there? So you multiply the cardinality, which is 4 times 4. 4 times 4, that's 16.
Let's think about building this permutation by choosing one at a time which of these elements goes into each one of these slots. How many choices for the number that goes into the first slot or the element? Well, we can choose any one of the available elements, so we have n choices. Having used up, let's say this element goes here. Having used up that element, we're left with n minus 1 elements, and we can pick any one of these and bring it into the second slot. So here we have n choices. Here we're going to have n minus 1 choices. Then how many we put there, we'll have n minus 2 choices. And you go down until the end. What happens at this point when
we are eventually going to reach a point where it would be n minus n, which is 0.
You are to pick the last element? Well, you've used n minus 1 of them.
So if you have to pick the last element in the set of n minus 1, that would be just 1.
There's only one left in your bag. You're forced to use that one. So at the last stage, you're going to have only one choice. So basically, the number of possible permutations is the product of all integers from n down to 1 or from 1 up to n. And there's a symbol that we use for this number. It's called
n factorial.
N factorial. So n factorial is the number of permutations of n objects, the number of ways that you can order n objects that are given to you. Now, a different question. We have n elements. Let's say the elements are 1, 2, 3 up to n. And it's a set. And we want to create a subset. How many possible subsets are there? So picking a subset means looking at each one of the elements and deciding whether you're going to put it in the subset or not. For example, I could choose to put 1 in, but 2 I'm not putting it in. 3 I'm not putting it in. 4 I'm putting it in, and so on. So, and that's how you create a subset. You look at each one of the elements and you say, okay, I'm going to put it in the subset or I'm not going to put it. So think of these as consisting of stages. At each stage, you look at one element and you make a binary decision. Do I put it in the subset or not? So therefore, how many subsets are there? Well, I have 2 choices for the first element. Am I going to put it in the subset or not? I have 2 choices for the next element, and so on. For all elements, we have, for each one of the elements, we have 2 choices.
So 2 raised
So
to power, that should be 2 raised to power n.
Overall number of choices is 2 to the power n. So, conclusion, the number of subsets of an n element set is 2 to the n. So in particular, if we take n equal to 1, let's check that our answer makes sense. If we have n equal to 1, how many subsets does it have.
Two.
So we're dealing with the set of just one. What are the subsets?
Not just so there is actually one more thing, that's null set. So null set can be a subset of this particular subset.
One subset is this one.
And then another is null.
Do we have other subsets of the
Yes.
one element set?
Yes, we do have.
Yes, we have the empty set. That's a second one. These are the two possible subsets of this particular set. So two subsets, when n is equal to 1, that checks the answer. All right. Okay, so having gone so far, we can do our first example now. So
the probability that 6 rolls of a 6-side die give different numbers of the outcome that made the event happen, number of the events in the sample space. Okay, so to define the sample space, okay, 6 rolls of a 6-sided. So I think I can solve this. We know that if we have a 1 die, we have sample space equals 6. There are 6 outcomes. For 2 dice, there are 6 raised to the power 2, which is 36. But in our case, we have 6 dice, so the sample space is going to be 1 over, no, not 1 over. It should be 6 raised to the power 6, which is a big number. I don't even know what 6 raised to the power 6 is. I think nobody does.
Given a die.
So the number of elements in the sample space, that equals 6 raised to the power 6. Number of the outcomes that make that make the event happen. What does that mean?
And we're going to roll it 6 times. Okay, let's make some assumptions about the rolls. Let's assume that the rolls are independent.
Okay, wait. 6 rolls. Okay, I might be wrong over here. We don't have 6 dices. I might be wrong, okay. Let's raise this up.
And that the die is also fair.
Okay.
So this means that the probability of any particular outcome of the die rolls, for example, so we have 6 rolls, one particular outcome could be 3, 3, 1, 6, 5. So that's one possible outcome. What's the probability of this outcome? There's probability 1/6.
1 over 6, 1 over 6, 1 over 6. So the probability of this particular outcome is 1 by 6 raised to power 6.
That this happens, 1/6 that this happens, 1/6 that this happens, and so on.
And you eventually multiply the even, so you get 1 over 6 raised to power 6.
So the probability that the outcome is this one is 1 over 6 to the 6th. What did I use to come up with this answer? I used independence, so I multiplied the probability that the first roll gives me a 2 times the probability that the second roll gives me a 3.
And if the events of these individual numbers won't be independent, then probably it would be a very complex question, still solvable, but it would be a pretty different or pretty difficult question as compared to in this case. That's why we have taken all the events to be independent of each other, so that the probability of getting each number should be 1 over 6, and getting this particular number 1 over 6 whole raised to power 6 is comparatively easier than getting some other number, which would be in the case of if the events would be dependent of each other.
And so on. And then I use the assumption that the die is fair, so that the probability of a 2 is 1/6, the probability of a 3 is 1/6, and so on. So if I were to spell it out, it's the probability that we get a 2 in the first roll times the probability of a 3 in the second roll times the probability of a 5 in the last roll. So by independence, I can multiply probabilities. And because the die is fair, each one of these numbers is 1 over 6 to the 6th. And so the same calculation would apply no matter what numbers I would put in here. So all possible outcomes are equally likely.
Equally likely. Yeah.
Let's start with this. So since all possible outcomes are equally likely, to find an answer to a probability question, if we're dealing with some particular event, so the event is that all rolls give different numbers. That's our event A. And our sample space is some set capital omega. We know that the answer is going to be the cardinality of the set A divided by the cardinality of the set omega. So let's deal with the easy one first. How many elements are there in the sample space? How many possible outcomes are there when you roll a die 6 times? You have 6 choices for the first roll. You have 6 choices for the second roll, and so on. So the overall number of outcomes is going to be 6 to the 6th.
Okay. So I was right.
So number of elements in the sample space is 6 to the 6th power. And I guess this checks with this. We have 6 to the 6th outcomes. Each one has this much probability. So the overall probability is equal to 1. Right? So the probability of an individual outcome is 1 over how many possible outcomes we have, which is this. All right. So how about the numerator? We're interested in outcomes in which...
We are getting all the numbers to be different. In that case, I guess it should be 6 factorial. Because you know, if I look at the event A, you know, we are getting 6 possible outcomes because they're saying that all give different numbers. So let's say we get a number 6 over here, then we can get a 5. This is probably one of the probabilities that I'm writing. No, wait. I think it should be 6 factorial. No, it's not 6 factorial. Um, I'm confused. I'm confused right now.
Which?
Let's just have a look at the solution. As far as I know, we can have 6 numbers, any 6 numbers. So I think it should be 6 factorial. But on the second place, you know, when we are going to roll the die for the second time, we should not have that number repeated. In that case, we would be left with 5 factorial. No, it should not be. Okay, wait. 6, then 5, 4. Okay, I think the probability of A should be 6 factorial only. Oh, that's a guess. That's a guess. Let's just have a look at the solution. What it says.
The numbers that we get are all different.
Okay.
So what is an outcome in which the numbers are all different? So the die has 6 faces. We roll it 6 times. We're going to get 6 different numbers. This means that we're going to exhaust all the possible numbers,
Exactly.
but they can appear in any possible sequence. So an outcome that makes this event happen is a list of the numbers from 1 to 6, but arranged in some arbitrary order. So the possible outcomes that make event A happen are just the permutations of the numbers from 1 to 6.
Oh.
So one possible experiment that's going to make our one possible outcome that makes our event to happen would be this. Here we have 6 possible numbers, but any other list of this kind in which none of the numbers is repeated would also do. So number of outcomes that make the event happen is the number of permutations of 6 elements, so it's 6 factorial.
So the answer to this particular question, the probability of this particular event in the question is basically 6 factorial by 6 raised to power 6.
And so the final answer is going to be 6 factorial divided by 6 to the 6th. All right, so that's a typical way that one solves problems of this kind. We know how to count certain things. For example, here we knew how to count permutations, and we use our knowledge to count the elements of the set that we need to deal with. Okay. So now let's get to a slightly more difficult problem. We're given once more a set with n elements.
Okay.
We already know how many subsets that set has,
All right.
but now we will be interested in subsets that have exactly k elements in them. So
So, we have this universal. What he's actually trying to say is, let's just decode that. We have this universal set omega, and we have n elements, these n discrete elements, or basically the subset. Wait, these are elements, not the subset. Okay. And then we might have these subsets. Okay. And the number of these subsets are basically k. That's what they're trying to say.
we start with our big set that has n elements.
Okay.
And we want to construct a subset that has k elements. Out of those n, I'm going to choose k and put them in there. In how many ways can I do this?
Wait.
N, I'm going to choose k and put.
So that should be nck. That should be n factorial by n minus k factorial times k factorial. What he's trying to say is that out of these n elements, out of these n things, or wait, what did it say?
We start with our big set that has n elements.
Okay.
And we want to construct a subset.
So out of these n elements, we want to construct k number of subsets. So it should be nck, which is n factorial over n minus k factorial. That's the formula, I think, times k factorial.
That has k elements. Out of those n, I'm going to choose k and put them in there. Okay. In how many ways can I do this? More concrete way of thinking about this problem, you have n people in some group, and you want to form a committee by picking people from that group, and you want to form a committee with k people, where k is a given number. For example, a 5-person committee. How many 5-person committees are possible if you're starting with 100 people? So that's what we want to count. How many k-element subsets are there? We don't yet know the answer, but let's give a name to it. And the name is going to be this particular symbol, which we
Okay, so that's combinator.
Read as n choose k. Yeah. Out of n elements, we want to choose k of them.
Okay. I think that's what we have studied in our high school. That's not a rocket science. That's easy to understand.
Okay. That may be a little tricky. So what we're going to do is to instead figure out a somewhat easier problem, which is going to be, in how many ways can I pick k out of these people and put them in a particular order? So how many possible ordered lists can I make that consist of k people? By ordered, I mean that we take those k people and we say this is the first person in the committee, that's the second person in the committee, that's the third person in the committee, and so on. So in how many ways can we do this? Out of these n, we want to choose just k of them and put them in slots, one after the other. So this is pretty much like the license plate problem we solved just a little before earlier. So we have n choices for who we put as the top person in the committee. We can pick anyone and have them be the first person. Then I'm going to choose the second person in the committee.
-1.
I've used up one person, so I'm going to have n minus 1 choices here. And now at this stage I've used up 2 people, so I have n minus 2 choices here. And this keeps going on. Well, what is going to be the last number?
1.
Is it n minus k? Well,
Okay.
not really. I'm starting subtracting numbers after the second one. So by the end, I will have subtracted k minus 1.
1. Okay.
So that's how many choices I will have for the last person. So this is the number of ways, the product of these numbers there gives me the number of ways that I can
just write up. I think I've not studied combinators in this particular way. I'm just gonna write that down in my notebook. So we are choosing K. That's the notation used for the first one. It's n minus 1 till n minus k plus 1. Okay.
create ordered lists consisting of k people out of the n that we started with. Now you can do a little bit of algebra and check that this expression here is the same as that expression. Why is this? This factorial has all the products from 1 up to n. This factorial has all the products from 1 up to n minus k. So you get cancellations. And what's left is all the products starting from the next number after here, which is this particular number. So the number of possible ways of creating such ordered lists is n factorial divided by n minus k factorial. Now, a different way that I could make an ordered list. Instead of picking the people one at a time, I could first choose my k people who are going to be in the committee and then put them in order and tell them, out of these k, you are the first, you are the second, you are the third.
Okay.
Starting with these k people, in how many ways can I order them? That's the number of permutations. Starting with k objects, starting with a set with k objects, in how many ways can I put them in a specific order? How many specific orders are there? That's basically the question. In how many ways can I permute these k people and arrange them? So the number of ways that you can do this step is k factorial. So in how many ways can I start with a set with n elements, go through this process, and end up with a sorted list with k elements? By the rule that when we have stages, the total number of stages is how many choices we had in the first stage times how many choices we had in the second stage. The number of ways that this process can happen is this times that. This is a different way that that process could happen, and the number of possible ways is this number. No matter which way we carry out that process, in the end, we have the possible ways of arranging k people out of the n that we started with. So the final answer that we get when we count should be either this or this times that. Both are equally valid ways of counting, so both should give us the same answer. So we get this equality.
Okay. All right.
Here. So these two expressions correspond to two different ways of constructing ordered lists of k people.
I'll go with the second one.
Starting with n people initially. And now that we have this relation, we can send the k factorial to the denominator, and that tells us what that number n choose k is going to be. So this formula, it's written here in red because you're going to see it a zillion times until the end of the semester. They are called the binomial coefficients. And they tell us the number of possible ways that we can create a k-element subset starting with a set that has n elements. It's always good to do a sanity check to formulas by considering extreme cases. So let's take the case where n is equal, where k is equal to n.
So where k is equal n, it should be 1.
What's the right answer
That's a special case.
in this case? How many n element subsets are there out of an element set? Well, your subset needs to include everyone. You don't have any choices. There's only one choice. It's the set itself. So the answer should be equal to 1. That's the number of n element subsets starting with a set with n elements. Let's see if the formula gives us the right answer. We have n factorial divided by k, which is n in our case, n factorial, and then n minus k is 0 factorial. So if our formula is correct, we should have this equality. And what's the way to make that correct? Well, it depends what kind of meaning do we give to this symbol. How do we define 0 factorial? I guess
0 factorial is basically not arranging anything in any possible way. That's what my intuition says. So in that case, there is only one possible way in which you don't actually arrange anything in any possible way. So that's only 1. So that's why 0 factorial equals 1. Maybe.
yes, in some ways it's arbitrary. We're going to define it in a way that makes this formula right. So the definition that we will be using is that whenever you have 0 factorial, it's going to stand for the number 1. So let's check that this is also correct at the other extreme case. If we let k equal to 0.
So if k equals 0, we're going to end up with the same thing. No. Yeah. We are going to end up with the same thing.
What does the formula give us? It gives us, again, n factorial divided by 0 factorial times n factorial. According to our convention, this again is equal to 1. So there's one subset of our set that we started with that has 0 elements. Which subset is it? It's the empty set. So the empty set is the single subset of the set that we started with that happens to have exactly 0 elements. So the formula checks in this extreme case as well, so we're comfortable using it. Now, these factorials and these coefficients are really messy algebraic objects. There's lots of beautiful identities that they satisfy, which you can prove algebraically, sometimes by using induction and having cancellations happen all over the place, but it's really messy. Sometimes you can bypass those calculations by being clever and using your understanding of what these coefficients stand for. So here's a typical example. What is the sum of those binomial coefficients? I fix n and I sum over all possible.
Try that on. What's wrong with this? Okay. So we're getting that sum from k equals 0 to n k. That should be 0 plus n1 plus n 2 till so on till n. So in that case, k equals 0, so there should be 1 plus um, should be n factorial by n minus 1 factorial times 1 factorial. So this whole thing can be written as n minus 1 factorial. That's 1, okay. And then you can write n factorial as n times n minus 1 factorial. So this and this gets cancelled out. So you get 1 plus n plus, if the value for n is 2, sorry, if the value for k equals 2, then you get n factorial by n what? N minus 2 factorial times 2 factorial, which is 2. So this translates to n minus 1, n minus 2 factorial divided by n minus 2 factorial times 2. So this n minus 2 and n minus 2 factorial gets cancelled out, and this particular we get n factorial by n minus n factorial by n factorial. So this is basically 1. So the sum of this particular series from k equals 0 to n is basically 1 plus n plus, wait, n times n minus 1 by 2 till so on till 1. Okay, I don't know what that equals to, but I think this particular value is maybe n factorial. Let me just write it. Let me just write the correct notation. Yeah. Okay.
Possible case. So
Okay.
if you're an algebra genius, you're going to take
I'm not an algebra genius. I'm pretty bad at algebra.
this expression here, plug it in here, and then start doing algebra furiously. And half an hour later, you may get the right answer.
Half an hour. Why?
But now let's try to be clever. What does this really do? What does that formula count? We're considering k element subsets. That's this number. And we're considering the number of k element subsets for different choices of k. The first term in this sum counts how many zero element subsets we have. The next term in this sum counts how many one element subsets we have. The next term counts how many two element subsets we have. So in the end, what have we counted? We've counted the total number of subsets. We've considered all possible cardinalities. We've added the cardinalities of how many, we've counted the number of subsets of size k. We've considered all possible sizes k. The overall count is going to be the total number of subsets. And we know what this is. A couple of slides ago, we discussed that this number is equal to 2 to the n. So nice, clean, and simple answer, which is easy to get, easy to guess.
So he's not going to prove that. How did we arrive at 2 raised to power n?
You give an interpretation to the algebraic expression that you have in front of you. All right, so let's move again to a sort of an example in which those binomial coefficients are going to show up. An example in which those binomial coefficients.
So probability of any sequence is p. Wait, what does that mean? It's Summation of k minus h sequence. Okay.
Coefficients are going to show up. So here's the setting. N independent coin tosses, and each coin toss has a probability P of resulting in heads.
Okay.
So this is our probabilistic experiment. Suppose we do 6 tosses.
Okay.
What's the probability that we get this particular sequence?
1/2⁶.
Of outcomes.
No, not 2⁶. So um, if the probability of getting a head is p, then probability of getting a tail should be 1 minus p. And they're talking about probability of getting a head, tail, tail, head, head, head. I think so, yeah. So that should be 1 over 4 2 raised to power p times 1 over 2 raised to power 1 minus p. So like the bases are, so you add them up. So that should be 1 over 2. Wait, that's 1 over 2. Wait, how's that possible? No, wait. No, 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 my bad, my bad. That's not the correct answer. So it's 1 over, for head, it should be 2 raised to power p. No. Oh shit. No, 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 no. So the probability of getting a head is basically 1 over p. For tails, it should be 1 minus p. For again tails, it should be 1 by 1 minus p. For these, I'm just gonna write the direct answer. It should be p raised to power 4 times 1 by 1 minus p raised to power 2. I think that should be the correct answer. I don't know, let's see.
Because of
Number of times of head. Oh, wait, it's not 1 over p, my bad. It's not 1 over p, it's actually p, it should be p raised to power 4 times 1 minus p raised to power 2. I think that's what they have written over here. That's what they have written here. So it actually means the number of times of heads times 1 minus p number of times of tails according to our whatever probabilistic model is defining. So in our case, if we see the number of heads, that's 4. So p raised to power 4, p raised to power 4, and then we are getting 1 minus p raised to power the number of times of tails. So we are getting 2. Yeah, that's correct.
independence, we
Yeah,
can multiply probabilities. So it's going to be the probability that the first toss results in heads, times the probability that the second toss
exactly.
results in tails, times the
Exactly.
probability that the third one results in tails, times probability of heads, times probability of heads, times probability of heads, which is just p to the fourth times 1 minus p squared. So that's the probability of this particular sequence. How about a different sequence? If I had four tails and 2 heads, but in a different order,
4 tails in a different order. Okay. It
let's
should be
say,
it should be same. It would be still the same. So that's p times 1 minus p times 1 minus p times p times p. So that's basically p raised to power 4 times 1 minus p raised to power 2. That's equals. It really doesn't matter if the order changes.
if we consider this particular
Since the in basically in the case of coin, the outcomes are equally likely. That's why nothing's changing over here.
Particular outcome.
So here in this particular probabilistic model, it's not exactly equally likely, but we actually see a symmetry over here because the probability of getting hits is p. So you get what I mean.
Would the answer be different? We would still have p times p times p times p times 1 minus p times 1 minus p. We would get again the same answer. So what you observe from just this example is that more generally, the probability of obtaining a particular sequence of heads and tails is p to a power equal to the number of heads. So here we had 4 heads, so there's p to the 4th showing up. And then 1 minus p to the power number of tails. So every k head sequence, every outcome in which we have exactly k heads has the same probability, which is going to be p to the k, 1 minus p to the n minus k. This is the probability of any particular sequence that has exactly k heads. So that's the probability of a particular sequence with k heads. So now let's ask the question, what is the probability that my experiment results in exactly k heads, but in some arbitrary order? So the
K heads. K, so we are getting k heads. P raised to power k.
heads could show up anywhere. So there's a
Okay.
number of different ways that this can happen.
Okay.
What's the overall probability that this event takes place? So the probability of an event taking place is the sum of the probabilities of all the individual ways that the event can occur. So
So this hashtag actually means the number of k minus head sequence times p raised to power k and minus k. What's n over here?
it's the sum of the probabilities of all the outcomes that make the event happen. The different ways that we can obtain k heads are the different sequences that contain exactly k heads. We just figured out that any sequence with exactly k heads has this probability. So to do this summation, we just need to take the common probability of each individual k head sequence times how many terms we have in this sum. So what we're left to do now is to figure out how many k head sequences are there, how many outcomes are there in which we have exactly k heads. Okay. So what are the ways that I can describe to you a sequence?
Let me just think of that. K heads. Okay. So let's assume we have n number of events. That's 1, 2, 3, 4 till n, and the probability of getting head. So by using this particular formula, this particular result, we can actually come up with a result of the probability of getting k times head. If we just plug in the values, the probability of getting k time heads, k times, that should be p raised to power k, since the probability of head is p, times 1 minus p raised to power. So what is 2? 2 is basically the left leftover number of events in which we are getting tails. So I guess it should be the total, which is n minus k. In this particular case, the n is 6. So 6 minus, how many times did we got head? So 4 minus 4, that equals 2, which fits in this formula. Not this. This is wrong, okay? This is wrong. Which fits in the formula. Oh, I think that's the final answer. Let me check.
With k heads, I can take my n slots that
Okay.
correspond to the different tosses.
Okay.
I'm interested in particular sequences that have exactly k heads. So what I need to do is to choose k slots and
Okay.
assign heads to them.
Okay.
So to specify a sequence that has exactly k heads is the same thing as drawing this picture and telling you which are the k slots that happen to have heads. So I need to choose out of those n slots, k of them, and assign them heads.
Heads.
In how many ways can I choose these k slots?
P raised to
Well,
power
it's the
k.
question of starting with a set of n slots and choosing k slots out of the n.
Okay, so starting with the n slots, and choosing k, that should be n factorial over n minus k factorial times k factorial.
Available. So number.
Okay, so this basically is the complex form of this particular thing. The formula that we are going to derive, he is basically deriving the whole formula, that how we arrived at this. I'm not even sure if this is even correct. I need to verify this.
Of k head sequences is the same as the number of k element subsets of the set of slots that we started with, which are the n slots 1 up to n. We know what that number is. We counted before the number of k element subsets, starting with a set with n elements, and we gave a symbol to that number, which is that thing n choose k. So this is the final answer that we obtain.
Okay, all right. Okay, n minus k. Oh, so I did some mistake in counting. All right. Okay, I get it. I get it.
So these are the so-called binomial probabilities, and they give us the probabilities for different numbers of heads, starting with a fair coin that's been tossed a number of times. This formula is correct, of course, for reasonable values of k, meaning it's correct for k equals 0, 1, up to n. If k is bigger than n, what's the probability of k heads? If k is bigger than n, there's no way to obtain k heads, so that probability is, of course, 0. So these probabilities only make sense for the numbers k that are possible, given that we have n tosses. And now a question similar to the one we had in the previous slide. If I write down this summation, even worse algebra than the one in the previous slide, what do you think this number will turn out to be? It should be 1, because this is the probability of obtaining k heads. when we do the summation, what we're doing is we're considering the probability of 0 heads, plus the probability of 1 head, plus the probability of 2 heads, plus the probability of n heads. We've exhausted all the possibilities in our experiment, so the overall probability, when you exhaust all possibilities, must be equal to 1. So that's yet another beautiful formula that evaluates into something really simple. And if you tried to prove this identity algebraically, of course, you would have to suffer quite a bit. So,
Okay. All right. I'm ready to suffer. I'm already suffering, you know. I'm already suffering. People who are watching this lecture are already suffering.
of course, you would have to suffer quite.
Wait, let me just see the timestamp. Well, people. I think that's the correct spelling of suffering. Yeah.
You would have to suffer quite a bit. So now, armed with the
Okay.
binomial probabilities, we can do the harder problems.
Okay. Coin tossing problems. Event B. 3 out of 10 were heads, given that B occurred. So B is any event. So B is a event, says that we have 10 tosses. So 2 raised to about 2. For 10 tosses, I guess the sample space should be 2 raised to about 10. And out of 10 tosses, 3 were hits. Okay, let's try to understand our. So we have 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And out of these, let me just think. Let me just think. 3 were heads. So I'm just selecting any random head, and other should be tails. So what is the probability of getting what is the conditional probability that the first two tosses were head? Oh my god, oh my god, oh my god. What did I just read? Okay, so what is the conditional probability that the first two tosses were heads? First two tosses were heads. Okay. And okay. What is the conditional probability? So for the first toss, it should be head. That's 1 over 2. For the second, it should be probability of getting a head given that a head has already occurred. Okay. Oh, that's a tough question, bro. Okay. What is the what's the conditional probability that first two turns per head are considered equally likely? Conditional law is uniform. The number of outcome in B out of outcomes in B, how many start with H? Ooh, okay.
So let's take the same experiment again. We
Okay.
flip
I think I need some time and to understand what is the probabilistic model is trying to say. Maybe I'm not able to do that on the camera, but yeah, off camera I can definitely do that.
coin independently 10 times. So these 10 tosses are independent. We flip it 10 times. We don't see the result, but somebody comes and tells us, you know, there were exactly 3 heads in the 10 tosses that you had. Okay? So a certain event happened. And now you're asked to find the probability of another event, which is that the first 2 tosses were heads. Let's call that event A.
Okay. So I can call this event A. Times probability of getting a head given that A has already occurred. And what is A? A is basically getting a head and head in the first. So I guess P of A should be 1 over 2. So this particular formula boils down to probability of A H intersection A divided by probability of A head and getting a head was the intersection, that's 1. So I guess this should be 1 and this is 1 over 2. So I guess this should be 2. No, wait. I think I'm doing some mistake. No, that's not possible. We are violating our probability actions over here. I think I'm doing some counting mistake over here. I think I should just focus on watching the lecture.
Okay.
Okay.
So,
All right.
are we in the setting of discrete uniform probability laws?
Whoa.
When we toss a coin multiple times, is it the case that all outcomes are equally likely? All sequences are equally likely?
Yes.
That's the case if you have a fair coin.
Okay.
That all sequences are equally likely. But if your coin is not fair,
okay,
of course, heads is going to have a different probability than tails. If your coin is biased towards heads, then heads is going to be more likely. So we're not quite in the uniform setting. Our overall sample space, omega, does not have equally likely elements. Do we care about that? Not necessarily. All the action now happens inside the event B that we're told has occurred. So we have our big sample space, omega.
All outcomes in the set B are equally likely. Probability p raised to power 3, 1 minus p raised to power 7.
Elements of that sample space are not equally likely. We are told that a certain event B occurred, and inside that event B, we're asked to find the conditional probability that A has also occurred. Now here's the lucky thing. Inside the event B, all outcomes are equally likely. The outcomes inside B are the sequences of 10 tosses that have exactly 3 heads. Every 3-head sequence has this probability. So the elements of B are equally likely with each other. Once we condition on the event B having occurred, what happens to the probabilities of the different outcomes inside here? Well, conditional probability laws keep the same proportions as the unconditional ones. The elements of B were equally likely when we started, so they're equally likely once we are told that B has occurred. So to deal with this problem, we need to just transport us to this smaller universe and think about what's happening in that little universe.
Okay.
In that little universe, all elements of B are equally likely. So to find the number, to find the probability of some subset of that set, we only need to count the cardinality of B and count the cardinality of A. So let's do that. Number of outcomes in B. In how many ways can we get 3 heads out of 10 tosses? That's the number we considered before, and it's 10 choose 3. This is the number in cardinality of A. So let's do that. number of outcomes in B. In how many ways can we get 3 heads out of 10 tosses? That's the number we considered before, and it's 10 choose 3. This is the number of
Okay. All right.
of 3 head sequences when you have 10 tosses. Now let's look at the event A. The event A is that the first 2 tosses were heads, but we're living now inside this universe B. Given that B occurred, how many elements does A have in there? In how many ways can A happen inside the B universe? If you're told that the first 2 were heads, so out of the outcomes in B that have 3 heads, how many start with heads, heads? Well, if it starts with heads, heads, then the only uncertainty is the location of the third head. So we started with heads, heads. We're going to have 3 heads. Question is, where is that third head going to be? It has 8 possibilities. So slot 1 is heads, slot 2 is heads. The third head can be anywhere else. So there's 8 possibilities for where the third head is going to be. Okay. So what we have counted here is really the cardinality of A intersection B, which is out of the elements in B, how many of them make A happen, divided by the cardinality of B. And that gives us the answer, which is going to be 10 choose 3 divided by 8. And I should probably redraw a little bit of the picture that I have here. The set A is not necessarily contained in B. It could also have stuff outside B. So the event that with the first 2 tosses are heads can happen with a total of 3 heads, but it can also happen with a different total number of heads. But once we are transported inside the set B, what we need to count is just this part of A. It's A intersection B, and compare it with the total number of elements in the set B. Did I write it the opposite way? Yes. So this is 8 over 10 choose 3.
Okay. And we're intersecting with the Murat comes to how when you start with edge, head and head. Okay.
Okay, so we're going to close.
How did we get 8? I'm not able to get this.
Well, if it starts with heads, heads, then the only uncertainty is the location of the third head.
Okay.
So we started with heads, heads. We're going to have 3 heads. Question is, where is that third head going to be? It has 8 possibilities.
Okay. Okay. So here's what they're talking about. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the 2 of the heads are fixed, and the possibility or the occurrence of the third head could be anywhere out of these 5, 6, and 8 positions. So it could be here or it could be here. Okay. and then we are intersecting, we are making, so in that case we would have total 8 cases. Yep, that gives us 8 cases.
So slot 1 is head, slot 2
Okay,
is.
okay, I
It
get.
happened with a different total number of heads, but once we are transported inside the set B, what we need to count is just this part of A.
Exactly.
It's A intersection B. Okay, so we're going to close with a more difficult problem now.
Okay, I'm gonna focus on this problem. Okay,
Okay.
partitions.
This business of n choose k has to do with starting.
Okay, so 52 deck of cards. So we have 52 cards. Okay. So let me just see deck of cards. What is ace? Okay, A. So that is A. So we have heart. I think this particular sign is called spade. This one is diamond. And okay, okay. And that tree like sign is club. Let me just draw that quickly. Okay. So we have ace. The diamond and the heart is red. The diamond and the heart is red. I have just highlighted it. This one is red and this one is red. And other two are blacks. I'm just gonna leave it in the yellow. And we have a ace over here, ace in this, ace card in this, and then this. Okay. Now let's get back to the each find the to 4 players. So we have 4 players, 1, 2, 3, 4. Probability that each gets an ace. Okay, because there are 4 aces and we have 52, so 52 C, the probability of getting the first person ace is basically 52C4, because out of these 4 cards, the first player could get anyone. Let's assume uh, the first player got this. The second player would be left with 52C3 and 52C2, 52C1. Okay, I think that should be our probability. I think so. And then what it says about the number of outcomes. What is the sample space? The sample space should be, no, wait. Out of 52 cards, we are using 4 cards. Okay. No, I think that's incorrect. I'm just mixing up some concepts. Yep, that's incorrect. Okay. It says that find the probability that each gets an ace. So person 1, person 2, person 3, and person 4. what is the sample space that we are defining over here? I think it should be 52, 52C4, because 4 is the total number of cards that we are taking out. Wait, no. What is this written? Are we like are we distributing every card or just 4 cards? I think we are distributing every card. If we are distributing every card, mm, the sample space should be 52. No, 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 no. Outcome. Partition of the 52 cards, number of outcomes. It says the number of outcomes is this 52 factorial by, okay, count the number of ways distributing the 4 races. 4 times 3 times 2 times 1. Dealing with the 48 cards. That's a little bit confusing, okay. No, I don't get this. I don't
With a
get this.
set and picking a subset of k elements. Another way of thinking of that is that we start with a set with n elements,
Okay.
and you choose a subset that has k,
Okay,
which means that there's n minus k that are left.
exactly.
Picking a subset is the same as partitioning our set into 2 pieces. Now let's generalize this question and start counting partitions in general. Somebody gives you a set that has n elements. Somebody gives you also certain numbers, n1, n2, n3, let's say n4, where these numbers add up to n. And you're asked to partition this set into 4 subsets, where each one of the subsets has this particular cardinality. So you're asking to cut it into 4 pieces, each one having the prescribed cardinality. In how many ways can we do this partitioning? N choose k was the answer when we partition in 2 pieces. What's the answer more generally? For a concrete example of a partition, you have your 52 card deck, and you deal, as in bridge, by giving 13 cards to each one of the players.
Exactly.
Assuming that the dealing is done fairly and with a well-shuffled deck of cards, every particular partition of the 52 cards into 4 hands, that is 4 subsets of 13 each, should be equally likely. So we take the 52 cards and we partition them into subsets of 13, 13, 13, and 13, and we assume that all possible partitions, all possible ways of dealing the cards are equally likely. So we are again in a setting where we can use counting because all the possible outcomes are equally likely. So an outcome of the experiment is the hands that each player ends up getting. And when you get the cards in your hands, it doesn't matter in which order you got them. It only matters what cards you have on you. So it only matters which subset of the cards you got. All right, so what's the cardinality of the sample space in this experiment? So let's do it for the concrete numbers that we have for the problem of partitioning 52 cards.
Honestly speaking, that's a really confusing problem. Yeah, it is. It is.
So think of dealing as follows. You shuffle the deck perfectly, and then you take the top 13 cards and give them to one person. In how many possible hands are there for that person? Out of the 52 cards, they're dealing as follows. You shuffle the deck perfectly, and then you take the top 13 cards and give them to one person.
All right.
In how many possible hands are there for that person?
So in that case, you're choosing 13 cards, any random 13 cards out of the deck of 52 cards. So it should be 54C13.
Out of the 52 cards,
Oh, yeah.
I choose 13 at
13.
random
Exactly.
and give them to the first person.
Exactly.
Having done that, what happens next? I am left with
We're left with 52 minus 13. That's how much? Um, wait, how much that is? It's 42. 42 minus 3, that's 39. So out of 39 cards, I have to distribute 13 cards again.
39 cards.
39,
And out
yeah.
of those 39 cards, I pick 13 of them
Exactly.
and give them to the second person. Now I'm left with 26 cards. Out of those 26, I choose 13, give them to the third person. And for the last person, there isn't really any choice. Out of the 13, I have to give that person all 13.
Exactly.
And that number is just
1.
equal to 1, so we don't care about it. All right, so next thing you do is to write down the formulas for these numbers. So for example, here you would have 52 factorial divided by 13 factorial times 39 factorial. And you continue, and then there are nice cancellations that happen. This 39 factorial is going to cancel the 39 factorial that comes from there, and so on. After you do the cancellations and all the algebra, you're left with this particular answer, which is the number of possible.
Okay, okay. So, all right. So let me tell you, this is what happening over here. So the total number of cards is 52, and we have to distribute 13, 13, 13. That's 13, okay, not 113. 13 to person 1, person 2, person 3, and then person 4. So what we are doing is for the person 1, we are distributing 52 cards. We are distributing 13 cards to a person. Now for the person 2, we are left with 39 cards, and we are distributing 13 cards out of this. For the person 3, we are to the person 3, we are still distributing 13 cards, but out of 26, say 13. And for the fourth person, which is B4, we have 13 cards left, and we are distributing 13 cards to him. So this is basically 1. Okay. Oh, so that's how we are arriving at that particular number. So 52 factorial divided by 13 factorial times 13 factorial times 13 factorial times 13 factorial. Okay, so on resolving this particular expression, we would get this, and that's our sample space. Okay, okay.
Partitions of 52 cards into 4 players, where each player gets exactly 13 hands. If you were to generalize this formula to the setting that we have,
Dealing with remaining 48 cards. Okay. Oh my God. Oh, that's a really good question. So, I can even explain how we arrive at this particular expression. So here's the thing. Out of the deck of 52 cards, we are actually removing the ace. So we have 4 ace, and we would left with 48 cards. Now out of these 48 cards, 12 would be distributed to person 1, person 2, person 3, and then person 4. Okay, okay, I get it. So in that case, it would be 48 C12. 48 minus 12 is what? 6, 3, 36 C12. And 36 minus 12 is what? 1. No, sorry, not 1. It's 24. It's 24C12, and then 12C12. This is 1 again. Okay, and by resolving this, we would eventually get a 48. 48, is it factorial if I'm not wrong? Yeah, that's factorial. 48 factorial divided by 12 factorial times 12 factorial times 12 factorial times 12 factorial. And this basically is the, let me just write that over here. So this is basically the way of RIBT, way of distributing those non-ace cards. And now we have to look the ways of distributing those ace cards. That would be 4 times 3 times 2 times 1 for B1, B2, B3, and for B4. And we just do the multiplication stuff that we have been doing. So it should be 48 factorial times 12 factorial times 12 factorial times 12 factorial times 12 factorial times this 4 times 3 times 2 times 1 divided by what was the sample space. I'm just gonna okay, let me write the sample space. I guess it was 52 factorial, 52 factorial by 13 factorial into 13 factorial into 13 factorial times 13 factorial. So that's a huge ass calculation, but I guess that's the final answer that we are going to get. Yep, exactly.
Here, the more general formula is you have n factorial, where n is the number of objects that you are distributing, divided by the factorials, the product of the factorials of the, okay, here I'm doing it for the case where we split it into 4 sets. So that would be the answer when we partition a set into 4 subsets of
So I totally get the idea of this. I totally get the idea.
prescribed cardinalities. And you can guess how that formula would generalize if you want to split it into 5 sets or 6 sets. Okay, so far we just figured out the size of the sample space. Now we need to look at our event, which is the event that each player gets an ace. Let's call that event A. In how many ways can that event happen? How many possible hands are there in which every player has exactly 1 ace? So I need to think about the sequential process by which I distribute the cards so that everybody gets exactly 1 ace, and then try to think in how many ways can that sequential process happen. So one way of making sure that everybody gets exactly 1 ace is the following. I take the 4 aces, and I distribute them randomly to the 4 players, but making sure that each one gets exactly 1 ace. In how many ways can that happen? I take the ace of spades, and I send it to a random person out of the 4. So there's 4 choices for this.
Exactly.
Then I'm left with 3 aces to distribute. That person already got an ace. So I need to look, I take the next ace, and I give it to one of the 3 people remaining.
Which is 4 factorial.
So there's 3 choices for how to do that. And then for the next ace, there's 2 people who have not yet gotten an ace, and I give it randomly to one of them. So these are the possible ways of distributing for the 4 aces, so that each person gets exactly 1. It's actually the same as this problem, starting with a set of 4 things. In how many ways can I partition them into 4 subsets, where the first set has 1 element, the second has 1 element, the third one has another element, and so on. So it agrees with that formula by giving us 4 factorial.
Factorial, yeah.
Okay, so there are different ways of distributing the aces. And then there's different ways of distributing the remaining 48 cards. How many ways are there? Well, I have 48 cards that I'm going to distribute to 4 players by giving 12 cards to each one. It's exactly the same question as the one we had here,
Exactly.
except that now it's 40.
Now instead of 52 cards, we have 42 cards.
8 cards, 12 to each person. And that gives us this particular count. So putting all that together gives us the different ways that we can distribute the cards to the 4 players so that each one gets exactly 1 ace. The number of possible ways, it's going to be this 4 factorial coming from here, times this number. This gives us the number of ways that the event of interest can happen. And then the denominator is the cardinality of our sample space, which is this number. So this looks like a horrible mess. It turns out that this expression does simplify to something really, really simple.
Okay.
And if you look at the textbook for this problem, you will see an alternative derivation that gives you a shortcut to the same numerical answer.
Okay.
All right, so that basically concludes chapter 1. From next time, we're going to introduce random variables and make the subject even more interesting.
That was hell of a show. That was hell of a show. What's the lecture 5? It's discrete random variables, probability, mass function, and expectations. Okay, it was a good lecture. It was a good lecture. I love the problems. Well, I guess that's it for today. Not for today, but that's it today for probability. And like here's like one more thing. I won't be doing reading material anymore because I really had to concentrate on understanding the stuff rather than just explaining it. So instead of doing that on the camera, I'm just gonna do the reading material off camera. Yeah, and I'm just gonna proceed with the lectures only with on camera. Yeah, that's so. Okay, so see you for any next topic that we are going to start. Okay, bye.